Hello, we are Team Seneka, and today we will show you our approach in the solution to the problem of semi competition, pulp and paper business logistics. We hope you like our solution. This is the outline for our presentation. The main objective of this project consists in evaluate a consortium that minimize logistic costs and stockouts. For this purpose, we have proposed different alternatives that we show later. Logistic costs can be divided in transportation costs, inventory holding cost, and penalties cost. On the other hand, the stockout is defined at the state in which a mill inventory is zero. The first step of the project consists in analyzing the data and assumptions. In relation with distribution, we assume an area of 100 per 100 mills, a number of 86 logging operations, one in each county, and the mills are located in the center as the figure shows. In our model, one important topic is the daylight hour. We define this taking into account the month as figure shows.
For the modeling of the trees and counties, we use the Ohio State Forest Inventory Report. Details of the information we used can be found on the appendix. As for the growth rate, we assume a constant rate of 73,000 tons of wood per county every year, which is roughly 992 tree seedlings per acre every year. To calculate the holding cost, we multiply the inventory by the fixed price of wood, then multiply by the holding cost. This cost we calculated as the WACC plus the standard carry cost of the pulp mill industry in the US. This value was found on this reference. This rate includes the cost associated to the risk due to damages in quality from extended storage periods, personnel costs, and other costs.
Other assumptions are explained in this slide and in detail in the executive summary.
We decided that simulation was the best approach to this problem. Due to its high complexity of interactive elements, its flexibility to evaluate alternatives and simulate capabilities for dashboards. The model is composed of 86 logging operations, the 3 mills, and square nets of paths we use to connect them all. A periodic process creates trucks when there is enough tons of wood available at the logging operation. Then it transfers the truck to the corresponding transfer node, which represents the logging operations. Then the truck will move through the link net to a random selected mill. When it exits the mill, the truck will return and will be destroyed. Every mill is composed of 3 servers, one for weight in, one for weight out, and one for the drop yard. This drop yard uses the crawlers as resources. This allows us to model the maintenance period of the crawlers. Every crawler will be blue colored when it's idle, green when it's utilized, and red when it's in maintenance. We can easily see the great queue of trucks that appears in the morning. We divided the processes into several categories. Every day, a timer will trigger a process which consumes a randomly generated amount of inventory in each mill. This process also detects if the mill enters to a stockout and will record this in several statistics. For the logging operations, a daily process will assign the number of truckloads and the weight of the truck for every logging operation, and another process will add the number of new tons of wood in each county. Finally, an hourly process will consume a certain amount of wood of the forest according to the constraints, such as the wood-rain ratio or if there is daylight, also depending on the truckloads allowed to send during the day. Each logging operation will accumulate tons of wood until it can send a truck. When this happens, it randomly assigns a mill and transfers the entity to the transfer node according to this link data table. One of our best tools for verification was the Simio dashboard. It allows us to visualize easily the inventory at each mill as a function of time. This dashboard facilitates to see and analyze the impact of any model change in the inventory or any other state variable. For example, to see how the inventory was affected by the bad weather in the months of April and May. For model verification, we used modular construction as it allowed us to fully test a module before adding another module. Once the model is complete, the animation will help us to check, for example, routine behavior or watch out for unexpected behavior such as blockages. To validate the model, we use the number of loads per day. For that, we created a random variable for the total amount of loads sent across all logging operations, and created a validation interval of this variable for every season. We do not consider the months from January to March, as this is the warm-up period. Using this validation method, we decided 15 replications at the standard number of replications. As we can see, the model falls inside the validation interval, and thus we can validate the model.
We have proposed 4 alternatives to address the solution in our problem. The first is not to do anything, which corresponds to the current situation. The other alternatives are framed in the consortium. The first is sectorization. Second, we propose sectorization plus dynamic pricing. And finally, sectorization plus dynamic pricing plus more than one law per county. Next, we explain these alternatives in detail. In our first alternative, every logging operation is assigned to the nearest mill, as the figures show. This logging operation only delivers to its mill assigned. In case that it is equal distance to various mills, the logging operation is assigned to the mill with most consumption rate. In our second alternative, we propose a dynamic pricing strategy. The figure shows the basis of this alternative. If the inventory level falls, then the wood price rises, and for this reason, logging operations price will increase. Our function is more sensible when inventory is near to penalization value. This allows the consortium react more efficiently in panic moments. Additionally, the logging operation supply changes according to the price elasticity supply as the reference and figure show. Finally, one important thing to mention is that this rule could help to increase the utilities of the consortium, because the wood average price will be lower than in the other alternatives. Our last alternative consists in dual sectorization plus dynamic pricing plus the building of more than one logging operation in 9 counties. This optimal value was found using UpQuest tool of Siemens software, as shown in the figure. Our results are divided in 2 categories. First, financial results in terms of costs, and second, operational results in terms of days lost due to stockouts. The main impact of the first alternative is reduce the total costs. As the figure shows, there is a reduction of 51% in the total costs in comparison with baseline model. However, this is not efficient on reducing stockouts because mills cannot access the production of all logging operations. When dynamic pricing is added, the costs remain the same, but there is an additional reduce of 30% on days lost due to stockout in comparison with the previous alternative, showing a more efficient reaction to panic moments. Additionally, when there are more than one logging operation in 9 counties, we assure that there are no stockouts. This is reflected in an alternative that is more expensive than the previous but anyway presents an important reduction of 33% in the total cost in comparison with baseline model. This graph shows how the main effect of our alternatives is observed by the significant reduction of penalization costs, approximately a reduction of 73% in average in comparison with the baseline model. The average inventory doesn't tend to change much between alternatives. However, for the last alternative, there is a significant increment of pay-per-take inventory, because this alternative creates more logging operations for this mill, thus generating lower risk of stockout as was observed previously.
We can see that production in every logging operation stays stable in the first 2 alternatives, which means that the only factor to change costs are the distribution of wood in the mills. Also, this alternative gives a greater total production, because there is less lost time traveling. The last alternative increases the production as it creates 9 more logging operations. In this plot, we can see a comparison of all the alternatives. In the left axis, we have cost performance, where between higher is the cut with the excess, the costs are lower. In the right axis, we have the stockout performance, where between higher the cut with the excess, the low stockout will have the alternative. In the x-axis, we have a weighted importance of avoiding stockouts. Selecting a high value means the decision maker is very averse to having a stockout. The 3 alternatives that dominate are these 3, and the decision maker must decide a stockout aversion coefficient that best suits his or her needs. If we assume a coefficient of 0.35, then the calculated performance of each alternative is the following, in which alternative 2 and 3 perform the best. As future work, we propose these improvements to the model, such as improve the dynamic pricing approach, like use historical data of the mills, add a non-linear supply price elasticity, and the evaluation of other functions to define the prices. We can also try to optimize other parameters of the model, such as growth rate, number of lows per county near Koala and Bright. We can also add granularity to the model, such as using continuous time like the flow library, and we can finally add possible unexpected events that may affect the tree growth, such as droughts, global warming, and forest pathologies.